Hey everybody. We're going to take a look at uh, one of our problems with 3D vectors, and it's the problem about finding the distance between two lines. So I've got the problem up here. We want the distance between the two lines given here, and we have the actual process is pretty quick. I mean, there's a few ways to do it, and some are quicker than others. The one that I'm going to do is actually a really quick way to do it, I think. But there is the understanding of why it even works, right? So it's going to involve a dot product, a cross product, and some division and addition. I mean, the cross product's the hardest thing in it, and we know that that boils down to just multiplication and addition and subtraction and stuff. And so it's not really hard to compute. But I want us to see if we can. I want to see if we can understand what's happening and why it works the way it works. So that's really what we're going to focus on. So the first job here is to decide exactly what it is we mean by the distance between two lines, right? So the way I think about it is I always imagine, like, I'm going to use my intuition here. If you look at any wall in whatever room you're in, and if somebody asked you how far you were from the wall, I imagine all of us would measure without even thinking about it. If we held a measuring tape from the point we're at to the wall, that measuring tape would hit the wall at a right angle, right? You wouldn't look way behind you to some faraway corner of the wall and measure that distance. We all kind of recognize, right? If there's a wall and I'm right here and you ask me how far I am from the wall, I'm not going to measure this distance. I'm going to measure this perpendicular distance. That's what we tend to mean by that, right? That's going to be our distance from the wall. It's also going to happen to be the shortest distance, right? You can see in this triangle that any other direction I choose, I can form this right triangle, and the hypotenuse has to be longer than this side. And since we can do that for every possible right triangle, that distance, that perpendicular distance, is going to be the shortest. So now we're trying to picture the same thing in space, right? We've got curves or lines that have, can have some kind of trajectories in space. And you wouldn't imagine picking points far away from each other and measuring them as their distance. What you end up doing is looking for a place where the line between them is at a right angle to both lines, okay? And unless these lines are parallel, which we've seen how to recognize by looking at the direction vectors, that there's only going to be one line between 2 points on them where it is where the line connecting them is perpendicular, right? And that's what we're going to call the distance. It is, again, going to end up being the shortest possible pairing of points, right? You could try infinite points where you take each point on the first line and pair it with any other point on the other line, and you could find all the distances between all the different points, and then do that for every line on every point on this first line, and eventually you'll find a place where the smallest distance to that point from all the other points on the other line is the smallest from all the times you did that, right? It's kind of confusing to think through. We'll be able to actually do this another way by the time we get a little further into our calculus course. When we learn how to minimize things of several variables, there's another method which we'll hit in a later video. But for now, we're going to use the geometry of vectors and lines and planes that we've been studying. So that's the idea. We're going to find this perpendicular distance. So I want to try now to get a picture of this better than the little scrawling that I can do here. So I'm going to put these problems. I've put these this problem. I've graphed it in our 3D grapher GeoGebra. So let me share that with you now. So let's see. All right. So right now what I'm looking at is those two lines. I've put their equations in. One of them is in red, one of them is in blue. I'm going to remove the axes first of all, because this picture gets a bit complicated to look at. So there's our two lines. You can zoom in and out. It's hard to know exactly how far away we are when we're just looking at lines. They look the same at any distance. So what I'm going to illustrate here is we're going to find this perpendicular vector, and we'll go through the actual computation. But remember what we want. We want a line that's perpendicular to both of them, right? And whenever we hear perpendicular to two things, a cross product springs to mind. And so what I've done first is taken the cross product of their two direction vectors and created a vector out of that I've called n. And I've put it so that I can move it along one of the lines pointing towards the other one, okay? So what I just want to show us is, here's an all right view of this. So there's that vector n. I think I'll remove that little name. It doesn't seem to help. Oops. Sorry, there we go. So there's our vector n that's perpendicular to both direction vectors. And notice right now it's pointing from the red line off into space, and it's not hitting that blue line, right? But if I slide it along the red line, at some point it's hitting both of them. It's hard to see, but right about there, somewhere in here, yeah, it looks like about right here, right? I'm not trying to find this exact spot right now. I just want the picture of it. It's now hitting both of those lines, right? If I look at it kind of down the direction of that vector, I can see it going through both of them, okay? So that's the distance, not the size of the vector, but if I connected these two, let's zoom in right there until it disappears, right? If I connected these two vectors with a little line segment in that direction, that's that perpendicular place, okay? So maybe this is still hard to see. Let me add something to this picture that may or may not help you, but we'll give it a try. For any 2 points in space, I can also, sorry, any 2 lines in space that aren't intersecting, I can find 2 planes, a plane for each line, a plane containing each line that also don't intersect. Right, so here I've got a blue plane containing the blue line and a pinkish plane containing the red line. And if we look at them from this direction, you can barely see the planes anymore because we're looking straight on. Those lines are lying in the plane and they're not intersecting with each other. Notice this direction, this perpendicular vector that I called n, is perpendicular to both planes. Right, it could be a normal vector for either one of the planes, right? It's sticking right out, oops, don't want to do that. It's sticking right out of them, right through both of them in a perpendicular way, right? And that, you might be able to reason for yourself why that would be, but I think we can see from the picture that that looks pretty clearly to be the case, okay? So there's our planes containing those vectors. Containing those lines, and this perpendicular vector is perpendicular to both of them. So now I want to keep adding some things to this idea. I want to find how much of that vector is between the 2 lines, right? How long is that little section, just the section between them, right? Just this little section between them, which would also be the distance between these 2 planes. One possible method for doing this kind of a problem is to find the equation of one of these planes and find any point on the line, the other line, right? So in this case, I could take, right, you could find the equation for this plane, I'll call this red plane P1, find any point on this line, and the distance from this line to the plane will be exactly the same as the distance between the 2 lines, right? And it's kind of clear in what's happening in this picture. Now there's all these places between the plane and the line, or really the plane and these 2 planes that are exactly the same as the distance between these 2 lines. Okay? But I'm not going to do it that way. I'm going to do it a little different way. What I'm going to do is now I'm going to find a vector connecting 2 points on our lines. Let me take the planes out for a moment. So the planes are off. I have a vector connecting 2 points on the line. I made one of the points the same place I'm drawing this vector n, the normal vector, but it doesn't have to be. And let's see. It doesn't matter which 2 points I pick, right? Notice I'm changing, I'm just drawing various vectors between these 2 points. And I can change either of these lines. I'm going to keep it at where I had it, where it seemed to be at the intersection point of them. Here's what I'm going to do with this vector, right? Because all I need to come up with this vector is a point on each line, which we have from their equations. I can project from that vector onto I'm trying to find a good viewing angle for this. Let me make one of them a little shorter, make it easier to see. Let's zoom in. All right, maybe this is a decent view of this. If I take the projection of this vector u, and I project it onto this vector n, I get the piece of u in the direction of n. In other words, I get this little vector, right, between these two. And the magnitude of that vector is exactly the distance between the 2 lines. So I'm taking this purple vector u and projecting it onto this gray vector n, and taking the magnitude of that vector. And we've worked out a formula for exactly this. We've called it the component of u in the n direction, right? Or the scalar projection of u onto n. And it gives us the magnitude of this vector almost, right? This can sometimes be negative, right? So for instance, if I have 2 vectors, one facing this way and one like this, if I take the projection, let's give them names, sorry. Here's u, here's v. If I take the projection of u onto v and take the component, the scalar projection, it will give me this distance. But if u happens to be aligned like this, it will give me this distance, except it'll be negative because it's saying it's in the opposite, that part of u is in the opposite direction of v, right? We don't want a negative distance, we just want the actual magnitude regardless of whether it's aligned with v or not. So what we'll actually compute the distance with is the absolute value of that component. And that's what I'm going to call the distance d between these 2 lines, right? So what that will look like, let me get rid of, oops, sorry. Let's get rid of this. That will be that green vector there, right? Or the green vector there is the actual projection, the vector projection, and we'll take the absolute value of the magnitude, or we'll take the magnitude of that, that vector, okay? So that's the setup. Maybe it'll help to see, I'll try one more time with the planes in there. It's hard for me to know what's going to help people see this, but what we're looking at is, oops. Hold on, let me reset here a little bit and clear those drawings. Okay. Maybe resetting didn't help too much. Zoom way out, find our place. Sometimes this thing is very difficult to manipulate the way I want. All right, I think now I'm getting more what I want here, kind of. I guess I'm too far away now. Let's zoom in. All right, I think I've lost it. I can't get myself into that good position anymore. But what I really want us to walk away from is this visualization of these 2 planes that contain the lines, and that if we project onto the normal vector between them, or sorry, the vector perpendicular to both lines that is between them, we're getting that distance. There's our location, right? That distance projected on to that little d. So let's actually do this computation now, okay? Let's see if we can actually make this work, because the computation itself is pretty straightforward, okay? So what do we need? I need a vector n, which is going to be perpendicular to R1 and R2. Well, that's fairly easy to come up with. If I take the direction vector, I'll call V1 the direction vector of R. That's going to be the vector 1, 6, 2. The vector direction vector 2, V2, is the direction vector for R2, is going to be 2, 15, 6. If I take their cross product, I'll call that n. So I've already computed n is 6, -2, 3. And now I want to take any 2 points between these 2 vectors, right? So I'll call this vector A. I want to take any 2 points between these 2 lines. Well, the easiest points to take are, let's take the points, let's write it this way. A will be the vector, let's say, from R2 of 0 minus R1 of 0. In other words, I look at where this line, the first line is at 0 and the second line is at 0, and take the difference between those two, right? Those are going to be pointing at 2 points on the line. I'll take the vector between them. So let's see what that looks like. R2 of 0, just putting in 0 for S, gives me 1, 5, -2, minus 1, 6, sorry, 1, 1, 0. So what do we get? We get 0, 4, -2. This is a vector between the 2 lines, right? That was that purple vector I had before. And so now all I need to do is the magnitude of the component of this vector between them onto this normal vector, this vector that's perpendicular to both of them. And we have a formula for this. We take their dot product divided by the magnitude of that perpendicular vector. And if you work this out, you get, let's see, the dot product between A and N. We get 0, -8, -6. The magnitude of N, just summing the square roots or the squares of these things, we get the square root of 49, which ends up being -14 over 7. And when we take the absolute value, we get 2. Okay, and that is the distance between those 2 lines, right? And specifically, what we mean is that perpendicular, the distance of that perpendicular line segment that connects both of them, or the shortest possible distance between the 2 of them. Okay, that's it for this video. Thanks, everybody.